Okay, great. I hope everyone can hear me and see me all right. So yeah, hi, my name is Matthew. I'm a postdoc here at Oslo, and I'm going to be talking to you today about the BeyondPlanck LFI processing that we have sort of been working on for the past couple of years, and that is the sort of precursor project to the Cosmoglobe project that we will be discussing at this conference. So the sort of the starting point for BeyondPlanck was, of course, the Planck DPC analysis, which I'm sure almost everyone here is familiar with. You know, we have power spectra and cosmological parameters, and for years it has been sort of one of the cornerstones of the field is all of the data that has been taken from Planck. And so in a lot of people's minds, the Planck analysis is mostly finished. And to a certain degree, that is true. But I mean, at the end of the analysis, there were still some outstanding issues that that with more time could have been better addressed. So one of these things, if we look, for instance, at these, so these maps here are Planck 30 gigahertz minus WMAP Ka band, which is the sort of closest analog to 30 gigahertz in WMAP. And so in the top here, we have the 2015 maps, and at the bottom, we have the 2018 maps. And you can see that these difference maps still have a fair amount of large scale power in them. And so this large scale power indicates that, at least in polarization, that the two experiments don't agree perfectly, right? That there is still disagreement about what the large scale polarization modes of the universe look like. And it's difficult to assign. There's been a lot of discussion in the field about what is causing these differences, and there's been some finger pointing and blame, but ultimately, this does indicate that there is a disagreement, at least fundamentally, between some of the experiments. And then another question that Ingen sort of touched on in her talk is this issue of the iteration. So if we look here at this plot, this is the gain as a function of time in the experiment for LFI. And so this black line is the gain solution that was published in 2015. And then if you look at the colored lines, the blue through the red lines are the 4 iterations that were produced for the 2018 release. And so you can see that the black line is far from this final red line, and that they are still evolving in time. And so one of the questions that we wanted to answer with BeyondPlanck is what if we had enough time to actually run this iteration process through to its logical conclusion? What would this converged gain, and for many other parameters, we're also still converging. This is just an example. And so what would the final converged solution actually look like? And so that's one of the things that we wanted to look at with BeyondPlanck. And another thing that we know to be an issue with both Planck and WMAP is that we know that there are modes on the sky that both of those experiments have done a poor job of measuring, just because of the way their scan strategies and the way that that they observe the sky. So this here at the top is the Planck 2018 30 gigahertz gain residual template. So this is basically a template that was fit in map space at the end of the analysis, and because we discovered this sort of large scale residual that was not accounted for by any of the other things that we were correcting for, and analogously, this is the WMAP K-band transmission imbalance template. So this is a very similar type of template for WMAP, and this is basically characterizing the modes that WMAP does a bad job of measuring. And so if we look again at these 30 gigahertz minus K-band difference maps, you can qualitatively at least notice that some of the features in this difference map look a lot like these two different templates that we know to be poorly measured modes in the two different experiments. And so the question is, could we use these two experiments to sort of constrain the modes from the other experiments? So could we use Planck to constrain these WMAP modes and vice versa? And if that's the case, how much better could we do with a sort of a joint analysis? So this is where we sort of started with BeyondPlanck. We wanted to see if we could address these issues in LFI by speeding up the iteration process that was performed for the 2018 analysis and performs hundreds of component separation and calibration iterations instead of just the 4 that there was time for at the time. We also wanted to see if we could break the internal Planck-specific degeneracies using external data, specifically WMAP, but also other data sets if they were necessary. And we chose the name BeyondPlanck to recognize that this work builds on and is a natural continuation of this official Planck analysis effort using some of the same techniques and tools, but also to emphasize that this involves not only Planck, but also other data sets in the field. So one of the reasons that this type of analysis is so hard is because of this thing that we're calling the chicken and egg problem. So we have, in CMB, we want to measure this actual data on the sky, right? Which is, this is what it looks like if you don't take the dipole out. And so what this is basically a linear combination of the dipole component and the galactic foregrounds and the actual CMB itself. And then, of course, to characterize that precisely, you also need to know your instrument calibration, which is a measure of your instrument's response to the signal itself. But of course, to know what your instrument calibration is, you need to know exactly what it is the instrument is measuring. But then, of course, to know what the instrument is measuring, you need to know the instrument calibration precisely. So this is, you have to know both of them to know the other one, which is one of the challenging parts of this analysis. So traditionally, the way an analysis pipeline has worked, you take the data from the satellite in this case, you perform calibration and map making, then you take those maps and you could do component separation, and then from the cleaned maps, you do your power spectrum estimation, and then you estimate your cosmological parameters, and then you take all of that and you publish it. But the thing that in BeyondPlanck we have tried to do, or that we think we have succeeded in doing, is this end-to-end iterative analysis. So instead of doing this loop once or having to rewrite the loop every time you want to change something, instead what we do is we feed back all of these products from the later stages of the loop back into the earlier stages of the loop for the next iteration. And so this iterative analysis is what allows you to get these thousands of iterations that we're talking about here, instead of the 4 that were allowed to do that we had time to do in 2018. So the main goals of the BeyondPlanck project were to implement this iterative end-to-end analysis framework for current and future CMB experiments using our experience on Planck. And then we wanted to demonstrate this framework with the LFI data because, as Ingrid mentioned, it's quite a self-contained data set and would allow us to implement a lot of the stuff without having to get really into the weeds of some of the outstanding systematics in other data sets. And then we wanted to make the software and results publicly available to the rest of the community. And sort of that's where we are now, is that we are very interested in other people coming in and collaborating and contributing to this process and helping us with other data sets that we haven't implemented yet. So this is the BeyondPlanck collaboration. We had 5 main EU-funded institutions, as well as some external collaborators at other institutions. And I won't go through all of the names because there's lots of them. But this is sort of the mathematical description of the pipeline. So what we do is we write down an explicit parametric model for our observed sky data. So this is our parametric model for LFI, but of course, for other experiments, you might want to include more terms, get rid of some of these terms that don't make as much sense, and so on. So it's quite a modularized process that you can include any effect that you need to, as long as you can model it. And then you let omega be the set of all of these free parameters. And then what you do is you derive the joint posterior distribution with Bayes' theorem. And that gives you this posterior P, which you can then map out with standard Markov chain Monte Carlo methods. And so in our case, we used a thing called Gibbs sampling, which we'll get to in a minute. But so for the explicit parameterization of our data model, so we have the D here, which is the raw data from the telescope, and then all of these components. So we have the sky model, which is the sort of standard sky model that has been used previously in other Planck analyses. We have the main beam term, the pointing matrix, the gain, the band passes, the side lobe pickup, the orbital dipole term, the correlated noise, and the white noise. And then if we look at the sky model more closely, it's made up of the CMB, a synchrotron contribution, a free contribution, an AME and spinning dust term, a thermal dust, and point sources. So this is what we implemented for the LFI analysis. But again, for other experiments, it might make more or less sense to use some of these terms, and that is easy to adjust if you need to. And then, as I said, you take omega, which is the set of all of these billions of different parameters that we have in this full distribution, and we use Gibbs sampling on it. And so Gibbs sampling basically is an MCMC algorithm that enables you to do one of these huge posterior distributions in a way that is tractable. So this is basically a cartoon of what Gibbs sampling is, for those of you who don't know what it is. So basically, it's an iterative sampling procedure where we explore the full probability distribution one variable at a time. So each sampling step, instead of drawing from the full posterior, instead draws from a conditional distribution and fixes every other variable other than the one it's sampling. And then you map out the entire joint distribution one sample at a time. So if we start with an initial guess from our probability distribution of A and B here, so if this red dot is our initial guess, and then we want to sample in A, we take a fixed value of B here, and we look at the conditional distribution A given this fixed B, which might look something like this, and then we sample from that distribution, and we draw our next sample here. And then we look at B given this fixed value of A, and say our distribution looks like this. Then we sample again from that one, and then we go back to sampling from A, and so on and so forth. And so in this case, with two variables, it's easy to visualize, but with millions of variables, obviously you can't do this in your head. But that's what the pipeline is doing ultimately. This is the Gibbs sampling algorithm. So what we want to do is this iterative analysis pipeline, and what we actually do is this. So this is the mathematical description of the pipeline, right? So we take each of these variables or sets of variables that we want to sample. So, the gain or the correlated noise or the spectral parameters or whatever. And then we draw samples from this distribution. So the probability of the gain, fixing all of the other variables in the system. And you do this effect many times. And so there are a couple main advantages of this. So one of them is that it's really easy to estimate quantities when you have statistically consistent estimates of the rest of the parameters. So that your all of the other parameters that you have fixed are at values that are consistent with the current parameter that you are drawing from, and so that really allows you to sort of subtract them or use them as a proxy for what that other signal should be. So if we look at this example here and we're estimating the correlated noise, for example. So this is the full sky signal from the LFI instrument, right? And if you want to take this time stream and estimate correlated noise from it, that's a very hard problem because it's got all sorts of other effects in it, obviously, right? But if instead you have access to an estimate of what all those other effects are at the current iteration, and then you can take that estimate and subtract it off naively, right? And then you're left with basically this thing here, which is what your current iteration thinks should be the residual from all of those other effects. And this is going to be much easier to estimate correlated noise from than this original signal. And so this is one of the main advantages of this Gibbs sampling approach, is that it becomes really easy to estimate signals because you already have estimates of all the other signals. And of course, this approach has been taken by many other experiments before. But a lot of the time, what you end up doing is if you want to subtract an estimate of your sky model, you have to take a fixed sky model to do that, right? Like you assume a sky model and subtract that off. Whereas this Gibbs sampling approach, because the sky model is integrated into your full sampling loop, you don't need to fix it, right? It will update itself every iteration, and it will still be able to map the full parameter space of your sky model as well. And so this leads us to basically our results. And to a certain extent, these results are going to be a little confusing to other people in the community who are used to having a set of maps and maybe a set of gain parameters and things like that. Because what we have instead is a full sample set of the whole iteration chain. And so for instance, here on the left here, you can see instrument parameters as a function of iteration. And here we have 6 different independent chains that are all running the same code. And so what you can see is that basically, so this is the chi-squared or the gain or the bandpass shifts or things like that, right? And so what you can see is that the sampling algorithm is basically mapping out the full parameter space of all of these samples and all of these parameters. And this enables you to do a bunch of things, like, for instance, looking at this gives you like basically the errors on all of these parameters as well, right? You have the full distribution of every parameter and the correlation between each of the parameters, which is something that is really hard to get with other techniques. And so in addition to these parameters as a function of time, we have this as well for all of the maps, right? So these are samples of the correlated noise for 4 different sample numbers. This is the synchrotron in Q, the CMB in Q, the synchrotron polarization beta, and so on and so forth, right? We have this for every single parameter in the whole chain. And so these sample sets are a lot more information than most people are used to from a CMB experiment. And so let's talk a bit about what data we have chosen to include. So because we wanted to make sure that the method was what we were highlighting here, we have chosen to include only data that would highlight the contribution of LFI, so that we could tell if our method was actually working and improving things over the state of the art. So we've used all of the LFI data at the time ordered level. So we're taking the raw data from the level 1 files and using that. And then we're using Planck 857 as a map to constrain the thermal dust intensity, Planck 353 in polarization to constrain thermal dust polarization. And then we're using WMAP 33 to 61 gigahertz in temperature and polarization to constrain the low frequency foregrounds. And then also we're including 1 Haslam band to constrain the really low frequency synchrotron stuff. And so what this means is that the intermediate HFI channels, so what's sometimes called the CMB channels in HFI, and the WMAP 23 gigahertz data are not included because they have much higher signal to noise than LFI. And so they would sort of swamp the end result that you got out and would make it really difficult to tell if our method was working properly. But of course, if we, in the future, we do intend to operate on these channels once the pipeline is more mature and we can incorporate larger data volumes like those. So this is an overview of what the computational resources required to run the pipeline are. So we compress the HFI data down to 860 gigabytes approximately. And that's small enough that we can read it all in on a single node of our compute cluster here at Oslo. And that really saves you a lot of time because you don't ever have to write or read from disk. Obviously, we do write to disk to save the results, but you never have to read in data again after your initial loop. And that means that this read-in time that would otherwise be a large contributor to the analysis loop is only done once. And then if we look at our total cost per sample, so that's one estimate of each of the free parameters in the system, and that costs us about 8,000 seconds, which is about 2.3 hours per sample on a 72 core node with 1.5 terabytes of RAM. And so this is obviously much less than the several months it took to run one sample in Planck 2018, and it's getting to a point where we can get like 1,200 or so samples. So in our case, we ran 6 independent chains of 200 samples apiece on 6 different nodes, and that we could get done in under 3 weeks, which was great. And so the total CPU cost for that was 220,000 CPU hours, which sounds like a lot. But if you compare it, for instance, to the Planck FFP sims, so one single FFP sim at 70 gigahertz cost about 10 to the 4 CPU hours. So this is already a significant fraction of the total time for our entire analysis run. So that means that this approach really is it's cheap when you compare it to some of the other sim-based approaches. So we have frequency maps from our analysis. So this is looking at the full sample set of the frequency maps. This is 100 different samples. And you can see that each of these frequency maps is a slightly different realization as the other parameters in the chain and update. But of course, you can also look at the posterior mean of all these frequency maps. And so that's what we have plotted here for 30, 44, and 70 gigahertz, and then in T, Q, and U. And you can see that these maps look, visually at least, very similar to what has been produced before from the LFI data. And so that's good. That means that the technique is working. And then we can also look at, because we have all of these frequency maps for every sample, we can look at difference maps between various samples. And so this is a difference between two different randomly selected samples. And so you can see that things are changing at about the 3 microkelvin level every sample. And so this sort of characterizes the width of your error ellipses on all of these parameters, basically. And so this is sort of a proxy for the uncertainty that we have in those final maps. And so if we go back to our differences between various experiments that we were talking about before. So this is, as you recall, the LFI DBC gain template. So these were the modes that we were pretty uncertain about in the original LFI analysis. And so if we look at the 2018 minus 30 gigahertz and the N-pipe minus 30 gigahertz, you could see that there are definitely some structures still left in these maps, and some of it does look like this template here. And so this means that we believe we are picking up at least some of the signal that has been characterized by this template. It's challenging to say from these plots who's doing a better job, but we'll look a little bit more at that here. So we look at the 30 gigahertz minus WMAP K-band. So this here is the 2018 analysis. This is the N-pipe analysis. This is us, and then this, as a reminder, is the WMAP imbalance template. And you can see in parts of the sky, you can see structures that look like this imbalance template quite strongly in this 2018 difference, and somewhat less strongly in N-pipe. And then we believe that these BeyondPlanck maps look the cleanest of these 3 difference maps compared to WMAP. And to a certain degree, that's somewhat expected because we are incorporating the WMAP data in our analysis. But this means that the method is working. We are getting better agreement by analyzing all of the data together. So we can also look at other results that we have. So these are power spectra from our maps, and you see that we're in quite good agreement with other people's power spectra that have been published. This is a zoom in of the sort of the white noise regime, and you can see basically 2 main effects. So black is the BeyondPlanck analysis. We have a flatter white noise spectrum, which means that we think that we have less correlated noise, and this is because we're doing because of the way that the component separation works. We're basically doing a multi-frequency signal estimation algorithm that was not done in these other analyses. And so that gives you a better handle on the correlated noise. And also, you can see at 44 gigahertz that we have a higher white noise level. And that's because in our current version of the pipeline that these plots are based on, we found some problems at 44 gigahertz that made us have to discard more data. And we're going to talk about that a little later in the TOD analysis talk that IDEC will give. And of course, we have other results. We have astrophysical foregrounds. So this is our synchrotron map, our free, our AME, and our dust estimates. And you'll hear a bit more about that later. And then we have many different samples of the CMB temperature. And there's obviously been some in-painting here in the galactic region, but these look very clean to us. And so we can look at our TT spectra. So this is the TT spectra at high L. And you can see that we are in very good agreement with previous analyses. There might be a slight disagreement right here, but other than that, we think that these TT spectra indicate that we have cleaned out all of the systematics that other people have also cleaned. So that's good. And so right now, what we're currently working on is processing the TOD at the diode level. So each of the feed horns in LFI was made up of 2 different feeds from different diodes that was for reducing the 1/f noise. And so if we read in the data at the diode level, this gives us more control over the low-level systematics. That way you can also incorporate corrections for these systematics in our Gibbs loop. So specifically, we're gonna do the 1 Hertz spike template subtraction in the loop. We're going to filter the reference load to remove some white noise, which is a trick that NPipe came up with, and so we're going to implement that. We're going to do our own corrections of the ADC nonlinearity terms, and we're going to iterate on the polarization angle calibration. And all of these things we're going to discuss in more detail in the later talks. So please stay tuned for that. And then you always want to close a talk with a forward-looking section. So the future is Cosmoglobe. So this is a depiction of our sky model. And we believe that we have successfully implemented this end-to-end analysis framework for global CMB analysis. But so far, only the LFI data has been fully integrated. And that means that the next step is to populate it with more data sets. So we are working on some of the public data sets like HFI and WMAP, and we're going to get started on FIRAS and Derby in the near future. But I mean, also a large portion of the data in the field is proprietary, right? It's owned by many experiments. And so this is sort of where Cosmoglobe comes in, is we're looking for basically for people to collaborate and come together as a field to try and use this framework to its full capacity, and make sure that the data that is needed to get the best possible sky model can be all analyzed together. And so obviously this is going to be a community effort, and will rely on active participation from people who are interested in that. So just a few words about our code base. So the main code is called Commander 3. It's a direct generalization to the TOD demand of Commander 2, which was used in the 2018 analysis. And you can find it on GitHub there. And there's many pages of documentation on the BeyondPlanck website. But of course, all of this software is currently under active development. So you're not going to be able to pick it up and immediately plug your data in, and it's going to work right away. And so we are happy to work with people to try and explain and help them integrate data into the framework, but it is going to be some work if you want to get involved. And so so if you're interested in collaborating or setting up some sort of joint project with one of the members of the team, we think that might be the best way of proceeding. So this is a big page of resources that you can go to. This will be in the slides that will be posted eventually, so you can look back at them there. So to summarize, we've successfully implemented this global framework for end-to-end Bayesian CMB analysis and demonstrated this on LFI. The framework has many important advantages. So you can do joint foreground and instrument modeling. You can do end-to-end error propagation. You can physically motivate your models. You can do multi-experiment analysis in the same run with the same code base. You can do goodness of fit tests however you like, and you don't have to email each other data files and then argue about the interpretation of those data files. And it has a very high computational efficiency. So you don't need a NERSC or anything like that to run one of these analyses. You can buy computers off the shelf yourself and do it. And so the next steps are to generalize and to populate this framework with as many data sets as are interested. And so that's why we're hosting this conference, to try and get people interested and excited about joining Cosmoglobe and working together on this open science-based community model of the universe. So again, we'd like to acknowledge the funding for BeyondPlanck, and I'd like to ask if anyone has any questions.